Up to this point, this course is focused on how to take derivatives. Now we're going to switch mode and say we've taught you everything. We're going to teach you about how to take them. Now we're going to use them to do different things. Okay, and it turns out there's a lot of stuff that we can do with derivatives. The first application that we have is the notion of rates of change. When you think about what a derivative is, calculating um, as we defined it, you got a function here, y equals f of x. It's defined by looking at, you're interested in right here, what's the slope of the tangent line, and what we do is we approximate it by a secant line, and we look at the change in the y divided by change in x, right? So we're looking at f prime of x equals a slope of a tangent line. Well, and I said this when I write it down, this is a change in y divided by a change in x. And there's two notions that we have here. The derivative is the slope of the tangent line, which we approximate with secant lines and then take a limit, right? The slope of the secant line you can think of essentially the average slope over that interval, and the slope of the tangent line is the instantaneous slope. Right now, what's the slope? Right? But still, either way, you're talking about a change in y over change in x. Now, when we draw these pictures, we say maybe we label the axes x and y, but quite often we don't ever put labels on them. We don't say, oh, this is one, or we might even label them with numbers, 1, 2, 3, but 1 what, 2 what, 3 what, inches, feet, meters, seconds, angstroms, what's the unit of measure that you're using? We generally don't say. But when I think about just finding a derivative, I'm thinking about this as whatever the labels are in this direction. If these are inches in this direction, then those are inches in that direction. And so when you're looking at your change in y divided by change in x, you're looking at like inches divided by inches, or feet divided by feet, or miles divided by miles. Whatever the unit is one way, this is the same the other way. And these essentially just cancel out. And so to say that if I tell you that, hey, at this point right here, the derivative is a half, means the slope of the tangent line is a half, so for every 1 I move over, I should go up a half, right? That's what I think of for slopes of lines. Now I'm going to start thinking of things in terms of rates of change. So for instance, this notion here, change in y divided by change in x, I'm going to think of it as the change in the output divided by change in the input. Okay. So for instance, if I have a function where this is going to be time and this is going to be population. Okay. So I might have a function that's, maybe I've been keeping some records and I've been looking at the population of a lemming colony, and on some island up in Alaska or something. Who knows? You do all these sorts of all these things, and we've got this data that's showing over time what the population of lemmings is at that time. So right here the population might be 50, and then right here the population might be 60 and whatnot. That somehow this is telling you population at any time. Okay. So when we look at now slopes of secant lines or slopes of tangent lines, I drew my function way too straight. Hang on a minute, I'm gonna draw a little bit different here, just to give myself a little more curve. I want it to kind of curve more. There we go, and then maybe do that. So I might be looking at here, at a point here, and saying, tell me the population at this time, tell me the population at that time. I can look at essentially the slope of the line between them. I can do a change in the output variable and a change in the input variable and look at what we have. Well, we'll look at the ratio of those things. Well, if I look at this change, you know, if the population here is 100 and the population here is 30, then the change was 70, right? But that's 70 individuals, right? 70 beings, 70 people, 70 lemmings, whatever. I think lemmings is what I was using. But down here now, this isn't lemmings, this is time. So how is time being measured? Is this days or hours or years or what? You know, maybe time, let's just say, is being measured in days, right? Just to pick something. So when I change from this time here to that time there, you know, maybe this was day 1 and this is day 5. You know, so the change in time there was 4 days. When I look at a slope of this secant line, what's going on down here? Slope of the secant line, well, it's 70 divided by 4, or whatever that is there, you know. But it's not just 70 divided by 4, it's 70 lemmings per day, right? That the labels are different here. I think of this as a rate of change. This is actually here now telling me population growth rate. This is saying that over a 4-day time, you're going to gain 70 lemmings. You're going to, whatever 70 divided by 4 is, what would that be? 35 divided by 2, so 17 and a half. So 17 and a half lemmings per day, right? 17.5 lemmings per day. That's the growth rate. That's telling me every day how much I should be expecting to gain. Now, it's the slope of a secant line. It's the average growth rate over that time. If I take a limit as the number of days here goes to 0, so you're looking at secant lines getting closer and closer to a tangent line, then you have what's called, so this is an average rate of change. Average rate of change. If I look at the slope of a tangent line, I get what's called the instantaneous rate of change. Slope of tangent line is instantaneous rate of change. Instantaneous. Boy, my handwriting is getting terrible here. Rate of change. You're saying getting terrible. It's been terrible. But okay. Instantaneous rate of change. Derivatives tell you slopes of tangent lines. But those tangent lines, if the input variable and the output variable have different labels, are often interpreted as a rate of change. How fast is your output changing per input? This is something that happens in a lot of different scenarios. Anytime you have time as your input variable, you have a rate of change in population per time. One example we're going to do a lot of in subsequent videos is if your input is position and your input is time and your output is position. So you've got somehow you're measuring some distance along an axis. I think of this as like mile markers along a freeway. So you tell me at time 0 you're at mile marker 7, and at time 1 you're at mile marker 9, and at time 2 you're at mile marker 10, and at time 3 you're at mile marker 10, and and so for each time, whatever time it is, whether you're measuring time in seconds or hours or days or millennia or whatever, you give me a time, I tell you a time, you tell me what position you're at, what mile marker on the road you're at. Then this is the type of thing I'm talking about, the position function. Sometimes it's measured height off the ground. If you think about throwing something up in the air and having to go up and come back down again. If you tell me what height it is at any time, then we're sitting in this position here. The input variable is time. The output variable is some sort of linear measure, so inches or meters or centimeters or miles or whatever, right? When I look at slopes here, you're talking about a change in the output variable. Well, the output variable is miles or feet or something. It's distance, right? This is distance. When you look at the change in the input variable, well, the input variable is time. Well, if you take distance divided by time, like miles divided by hours, miles per hour, that's speed or velocity. Velocity. So if I have a position function where the input is time, then the derivative of that position function, the rate of change of that position function, is the velocity. When I say that I'm traveling at 50 miles per hour, if the speedometer tells me 50 miles per hour, it's not that the car has said, hey, I've been keeping track for the last hour and you've traveled 50 miles. It's like, no, it's telling you a slope of a tangent line saying, right now, instantaneously, if you kept going at this speed for an hour, you'd travel 50 miles, right? The slope of the tangent line is 50. This is something we'll do a lot of examples of. We'll come back to that. I want to just give you an overview of sort of the different types of things that you'll see. In economics, they quite often do things where your input is the number of things produced. So you might be making washing machines, and you want to know, if I make 7 washing machines, what's it going to, and then, okay, so what's the output? What is it going to cost? How much profit am I going to get? I mean, there's different functions that you might have here, but for instance, let's just pick cost. So cost is going to be in dollars, right? So you have this function that looks, who knows what it looks like, but actually cost functions quite often look something like this. There's an initial, how much does it cost to make 0 things? Well, you actually have to make your factory, you got to buy the equipment, so there's some startup cost here that before you even produce anything, you've got some cost. But then, to produce that first, to produce 1 unit, then you have the cost of the startup plus the labor plus whatever power it takes, whatever, and then to produce the next unit, you've got some more cost. Anyway, so you look at how much does it cost for the number of things that you produce. When they then start looking at derivatives here, they use derivatives where, oops, that's not what I wanted. I wanted something to write with. So, of course, I'm drawing in secant lines here. These are average rate of change, and the tangent line, it's the slope of the tangent line, is the instantaneous rate of change. But the idea here is you're taking a change in the output variable. Here, this would be dollars, and the input variable here is the number of things I'm producing. So these would be, like washing machines. This is per unit produced here. So when I look at a slope, dollars per unit, I'm saying, I might produce, to go from here to here, it might be, I've already produced 10, and now I'm going to up the production to 20, so there's a change of 10 there. How many dollars of change? Maybe it was, $300. So $300 for that increase of 10 would be $30 per unit, right? So the average of going from here to there, the average cost was $30 per every unit. If I said, what is it right here? If I'm producing 10 right now, what does that next unit cost me? Well, the next unit costs you whatever the slope is right there. Okay, and so when they start looking at dollars per unit, they're looking at derivatives of cost functions, or they might be looking at profit. How much profit am I going to make from that next unit? when you're in an economics class and they start doing these using derivatives to talk about this stuff, they don't use the word derivative. They use the word marginal. They say marginal cost, right? Or marginal revenue or marginal profit. They use that word marginal to mean what would the cost of one more thing be, or what would the profit from one more thing be? What's the marginal cost? What's the marginal profit? And what they're talking about is they're talking about the derivative. They're saying cost per unit, dollars per unit, or profit per unit. And that's the notion of the derivative. Right? The derivative is used in so many places. Anytime you're looking at how fast something is changing, you're talking about a derivative. Okay. I'm going to leave it at this and make some more videos with individual examples of these different types of things.